Hello, am I audible? Hello, can you hear me? Okay. Okay, so we'll start now. Uh, Good evening. My name is Ranjan Bora, and I am one of the TA in this course, Biomechanics of Joints and Orthopaedic Implants. This course is instructed by Professor Sanjay Gupta from IIT Kharagpur. And from the starting of the course, I have been taking the tutorial lectures every Friday, like in this time from 6 p.m. to 8 p.m. And I have already taken six tutorials for the past 6 weeks and also uploaded those videos in the YouTube channel, in my YouTube channel. And you can find the links to those videos from the NPTEL website of this course. I hope you are going through those videos. Means I have discussed about different concepts from this course and also solve some numerical problems. Those will be helpful for you if you are appearing in the final examination. So today I will first solve the assignment from week 6, last week assignment. And after that, I will discuss some concepts from week 7 and I will also solve some numerical problems using those concepts. So first, first I will first I will solve the assignment from week 6. Okay. So yeah, this was the first question in the week 6 assignment, which is partial volume effect results in the loss of apparent property in FE model because of the limited resolution of the imaging system. Is it a true or false statement? So it is a true statement, like using the partial volume effect, we lost some properties in the FE model because due to the limitations in the imaging system, like you can see a finite element may overlap two or more different bone tissues. And in the partial volume effect, we average the voxel values on both sides of the boundary. And this results into underestimation of the material properties of the element. And this effect is known as partial volume effect. So this statement is true. So option A is correct. Next question, who is considered as the father of modern total hip total arthroplasty? So option A is correct. Sir John Charnley is considered as the father of modern THF. Okay. Coming to the next question, the failure scenario arises due to wear particle debris from articulate surface known as, which option is correct? You can type your answer in the chat box if you know or if you have submitted the assignment. So the option B is correct. The failure scenario arises due to air particle debris from articulate surface. It is known as the particulate reaction failure scenarios. And it is due to the generation and migration of air particle debris from articulating surface. Material interfaces gradually disintegrates, causing eventual loosening. So here you can see in the figure, because of the here the air particle debris are there, and uh, because of the accumulation of this air particle debris, means the materials between the implant and bone interface gradually disintegrates, and this eventually causes the loosening, implant loosening. So this option B is correct, articulate reaction. Now this question is implant bone interface failure due to debonding. Which option is correct? Option D is correct. Implant bone interface failure due to debonding depends on the local bone strength and the local interfacial stresses. This coming from this Hoffman's equation. This equation is for composite failure of composite material, because when we place a implant inside our bone, so this acts as a composite material because this implant has a material property, different material property than the surrounding bone. So if E1 is the Young's modulus of the implant and E2 is the Young's modulus of the surrounding bone. So because of the difference in material properties between the implant and the bone, we can consider this whole system as a composite. And so we can apply the Hoffman's failure criteria like this equation. In this equation, this x represent the strength values in the x direction, and y represent the strength values in y direction. P and C represents tensile and compression, and sigma 1, sigma 2, and tau 1 to are the stresses, and S is the shear strength. So using this equation, we can evaluate the value of FL. Now, if the value of FL equals to or exceeds 1, then we can say that there will be some failure. We can expect some failure. So using this equation, we can estimate the failure in implant bone interface. Okay. Next question is, the CT attenuation value of bone is approximately. What is the answer? You can see this table, like for different item, these CT values are given in Hounsfield units. So for bone, it is the range is between 400 to 1000. So option A is correct, 500. Okay. And the next question is, dash implants facilitate the bone ingrowth on implant surface and stable fixation occurred through. In this question, option A is correct. Porous coated implants facilitate the bone ingrowth on implant surface and stable fixation occurred through osseointegration. And next question is, major reason for the stress shielding is. So you can see why there is a stress shielding after putting an implant inside the bone. So it is because of the mismatch in the material properties, stiffness values between the implant and the bone. Carried by bone, and this alters the load transfer pattern across the implanted bone. Consequently, a significant portion of bone which was exposed to loads in intake condition is shielded from carrying the load by a stiff prosthesis in the implanted condition. Mm, My screen is not visible. Let me see. Is my screen visible? Okay, now it is coming. So the major reason for the stress shielding is discontinuity in stiffness of implant and bone. Option B. Now, next question. Stress shielding decreases with a decrease in. So we have seen in the previous slide, stress shielding occurs because of the difference in stiffness values between the implant and the surrounding bone. Because implant is made of metal, and generally metal has a very high stiffness value, which is around 110 to 200 gigapascal. But bone is a softer material compared to implant, and it has a very low stiffness values around 16 to 20 gigapascal. So now to reduce the stress shielding, like we can decrease the stiffness of in the implant, then the difference will also get decreased. So option B is correct here. Stiffness, by reducing the stiffness of the implant, we can reduce the stress shielding in the bone. Next question is, possible direct sources of generation of wear particle debris are. Here you can see the possible sources of generation of wear particle debris are wear of acetabular bearing surface, then abrasion of cement, implant, and bone interfaces, and fretting between metal parts in modular prosthesis. So option D is correct. It has all the options. The next question is a modeling of cartilage layer at articulating surface in FE modeling of pelvis increases the stress concentration. So is it a true or false statement? It is a false statement. Here you can see the results. So after doing the FE modeling of pelvis, in the first figure, they have also modeled the cartilage layer. And in the second femur, like difference between the first and the second is here. The first, it is the femoral head is anatomical, but in the second, the femoral head is spherical. And in the third figure, the femoral head is spherical with no cartilage layer. So when they did not consider the cartilage layer, you can see the stress values are higher, like it is around 57 megapascal. But when they consider the cartilage layer, the stress values are uh, less than the maximum in these two cases. So the modeling of cartilage layer, it does not increase the stress concentration, else is decreases the stress concentration. So it is a false statement. Option B. Okay. Next question is digital image correlation method helps to measure. So why do you use the digital image correlation method? So DIC is a non-contact optimal metrology to measure full field surface deformations on practically any material subjected to driving forces. In this figure, you can see here we are using the DIC method to measure the full field surface deformations. They are using this high resolution camera through which they can measure the deformations of any practically on any surface which are subjected to driving forces. So we measure mainly external strain distribution. Next question is, which of the following is not a procedure involved in finite element modeling of bone? So here, four options are given in the thresholding and region growing, which method are used while segmenting the STL images from the CT scan data. And contour detection also is one of the method in the segmentation process, but digital image correlation is not a method which we use in the finite element modeling. So like in this figure, you can see here reconstruction of femur based on the CT scan image processing. Here they are using thresholding, region growing, and contour detection. So option C is here correct. We don't use the digital image correlation method in the modeling of finite element of bone. Now next question is linear displacement sensors measure dash of an implanted bone specimen. So with the help of linear displacement sensors, like in this figure, you can see here is one linear displacement sensor, and here is one, and here is one. So by putting this linear displacement sensor, we measure the relative implant bone micromotion, like relative displacement between the bone and the implant. So option C is correct. And next question, which technique is generally applied to simulate physiological high compressive loads on the human spine? We use the follower load technique. Here you can see in the follower load technique, here axial compressive loading changes the curvature of the spine, evoking bending moment. Follower load technique is generally applied that follows the curvature of the spine and is used to simulate physiological high compressive loads on the human spine. And these compressive loads represent the load carrying capacity of the human spine and play an important role in maintaining its stability. So option B is correct. Next question, what surgery is used to join two or more vertebrae together to prevent motion in the destabilized segments of the spine? We use the fusion surgery. In this, we use one interbody case, then we use the pedicle rod and screw uh, to fuse two or more vertebrae together. So option A is correct. Okay, next question is dash and dash are few of the requirements of speckle pattern DIC measurement. So for the speckle pattern DIC measurements, these are the requirements. Like it should be non-repetitive, the material should be isotropic, the light should be of high contrast. So here option A is matching, non-repetitive and high contrast. And next question is, what is the most prevailing failure scenario of cemented hip stem? So accumulated damage is the most prevailing failure scenario in which it is based on gradual accumulation of mechanical damage in materials and at the cement implant bone interfaces due to excessive stresses leading to loosening and failure. Option A is correct. Next question is apparent density of bone is generally assumed to follow a relationship with the CT gray value. So it is assumed to follow a linear relationship. Like this is the equation. This is rho is the apparent density of bone, and rho one is the density of water, and rho two is the density of cortical bone. So it is a linear relationship with CT gray value, which are which are represented in the Hounsfield units HCO. Okay. Next question is minimal bone resection is one of the merits of total arthroplasty over resurfacing arthroplasty. So is it a merit or demerit, like minimal bone resection for total arthroplasty compared to resurfacing arthroplasty? It is not a merit, it is a demerit. So it is a false statement because here you can see we have some advantages of hip resurfacing arthroplasty than the conventional total hip arthroplasty, which is the minimal bone resection and more precise biomechanical restoration, more physiological stress distribution, and easier revision. So in the question, it is saying merits of total arthroplasty over resurfacing arthroplasty. So it is a false statement. Next question is, does this stem length affect the strain distribution in the implanted femur? Yes, the stem length will affect the strain distribution in the implanted femur. Here you can see strain distributions for two femurs for two types of stem length. Like first figure is for the long stem length, and the second figure is for a short stem. And you can see for both the two cases, the strain distribution is not same. Like the color map, you can see the color maps are not matching. There is difference in the color maps. So it affects the strain distribution in implanted. Means the strain distribution depends on the stem length of the implant. So it is a true statement. Okay, so that was the assignment from last week. Now I'm going to explain some concepts from this week and also from some concepts from last week, and also I will solve first explain the concepts, and after that I will solve some numerical problems using these concepts. So first one is the stress shielding or bone remodeling. So what causes this stress shielding? So main reason for stress shielding is the implant is stiffer than the native bone, uh, and it carries the bulk of the load, which was formerly carried by the bone. This alters the load transfer pattern across the implanted bone. And consequently, a significant portion of bone which was exposed to loads in intact condition is shielded from carrying the load by a stiff prosthesis in the implanted condition. And this sudden change in stress strain distribution is known as stress strain shielding. So here you can see when we place an implant in the bone, femur bone, and whatever the hip reaction force coming and the head of the femur, like most of the load carries by the implant, and the small amount of load gets transferred to the bone. And because of this, like there like initially this bone was carrying the whole amount of load which was coming from the hip joint, but after putting the implant, the load is getting reduced. So as a result, there is as a result, because of the inactive in the bone, like inactive in the bone tissue for to accept the load, here it's some in resorption in the surrounding bone. Because if there is no load, then in that part, some bones gets resorbed. So this phenomenon is known as stress yielding. Okay, main reason for stress yielding is difference in the stiffness values of the implant and the surrounding bone. Okay, so now we'll see two examples of stress yielding. Like we have seen why the stress yielding happens, but we can also see what the consequences of uh, placing an implant in the bone, like what happens to the load carrying capacity of the bone. So load carrying capacity and stress carrying capacity. So in the first figure, you can see this is a intact healthy bone. Like there is no implant. And in the second figure, you can see there is one implant. Means one implant is put in the bone. So initially, this same amount of load is acting, 50 Newton and 50 Newton. So what happens to the load carrying capacity? Like, so in the first case, the bone is carrying whole 50 Newton of load. But in the second case, this 50 Newton is getting divided between the bone and the implant. So we need to find out those values. Like if we assume that FB is the load carried by bone and Fi is the load carried by this implant. So what is FB and what is Fi? So first we need to find that, and also we'll find the stresses. So in the first figure, first image, 50 Newton is acting in the downward direction, means it is compressive load. So we will find out the compressive stress, sigma compressive. What is the definition of stress? Force divided by area. So force is 50 Newton. Area is, for section is given 10 mm square. 10 Newton per mm square. So if we do this, it will be 5 megapascal. Okay. So 5 megapascal is the stress, compressive stress when there is no implant. But uh, but when there is implant, what are these stresses? Sigma B and sigma I. So we'll do this problem now. Here, let us assume that 50 Newton is getting divided. Here it is FB and here it is Fi, and we'll assume because of the compressive load, the bone and implant is getting compressed by a distance displacement delta. Okay. So since 50 Newton is getting divided into FB and Fi, so we can write FB plus Fi equal to 50. And since bone and implant, they are in contact with each other, so and there is bonded, means implant is bonded with the bone, so they behave like a composite type of material, and because of that the deformations will be equal. That means the deformations in bone is equal to the deformations in the implant, because this delta means the bone and implant, they are getting compressed by the same value, by the same amount of delta. So now this delta we can write using equations. We know that from Hooke's law, stress is proportional to strain. So stress equal to Young's modulus multiplied by strain. And what is stress? Stress is F divided by area. And Young's modulus. What is strain? Strain is delta divided by actual length. So from here we can write delta equal to FL by EA. Okay, now we can put delta here. Delta of bone is FB dot L divided by EB dot A. Since cross section is equal, cross section of each layer is 5 mm square. So I am writing the means cross section as cross section. I'm using the symbol A for cross section and symbol L for length. Length is also same for both in bone and implant. For implant, it is Fi dot L divided by EI dot A. So L and A will get cancelled from both sides. So FB equal to EB divided by EI dot Fi. Now we can use this equation 1. We can substitute the value of FB here and we will find the value of Fi from that equation. So if we substitute, then we can take Fi common. EB FB divided by EI plus 1 equal to 50. Now if we substitute Fi, EB is Young's modulus of bone is given 20, Young's modulus of implant is 200 plus 1, 50. So if we do this calculation, we'll get Fi is 45.4 Newton. Okay. So using equation 1, we can find FB, which will be 50 minus 45.4, which will be 4.6 Newton. So you can say when there is no implant, then whole 50 Newton load was taken by the bone. But when we place an implant, this 50 Newton load is getting decreased to 4.6 Newton. So significant reduction in the load carrying capacity of the bone. So because of this, stress shielding happens, resorption in the bones surrounding the implant. So now we can estimate the values of sigma B and values of the compressive stresses in the bone and implant. So compressive stress in bone is FB is 4.6 divided by 5. If we do this, it is 0.9 megapascal, and sigma I is Fi is 45.4 divided by 5. It is 9.08 megapascal. So these are the answers. Sigma B is 0.9 megapascal and sigma I is 9.08 megapascal. Okay. So next is so we have seen that the stress shielding happens because there is the difference in stiffness values of the bone and the implant. So how we can reduce the stress yielding? So to reduce the stress yielding, we need to reduce the stiffness of the implant. So for reducing the stiffness of the implant, there are two case. Like case one is we can reduce the stiffness of the implant by reducing the Young's modulus of the implant. So we can use a porous implant. You can see this equation. So this equation is coming from which we have already derived, this FB plus FI equal to 50. If we substitute FB in terms of FI, so here in this equation, you can see Fi multiplied by EB divided by EI plus 1. And in the example, the area was same, area of the bone which is equal to area of the implant. That's why this area terms, this got cancelled. But in general, these terms will also appear in the equation. So here, if we reduce the implant of the, if we reduce the stiffness of the implant, so here you can see if we reduce this stiffness, then numerator uh, this denominator value is getting reduced. So overall, this numerator value is overall this equation value will getting increased, and F implant means the value inside the bracket will get increased, and if we then evaluate the F implant, then it will keep on decreasing. Okay, this is one case, and the second case is we can reduce the cross-sectional area. So again, in this equation, in the denominator, we have two terms. One is stiffness and one is the area, cross-sectional area. So by reducing the cross-sectional area, this overall values of this ratio is getting increased, and as a result, this F implant will keep on decreasing. So these are the two methods using which we can reduce the stress yielding in the implant. Now there is one problem. This problem is related to stress strain, like uniaxial compression test. So in this problem, it is given a hypothetical uniaxial compression test was performed on a machined cylinder of human femoral cortical bone of 6 mm diameter, and the results of the force displacement measurements are shown in figure. Estimate the elastic modulus and the ultimate strength of this sample of the bone. So the cross section of this bone is given is cylinder, that means circular, and the diameter is given 6 mm. We have to find out the elastic modulus and the ultimate strength. So what is the elastic modulus? It is the slope of stress strain curve. So force displacement curve is given. So if we divide the force with area, we'll find the stress, and if we divide the displacement with the length, we'll get the strain. So here first we have to find out the slope of this linear part, of this stress strain curve. So here, we have to figure out 1 point, coordinates of 1 point. So here we can take around 3,500 Newton stress, and in 3,500 Newton stress, we are getting a displacement of 0.09. So we'll take these values, two values, 3,500 500. Okay, so how we will find the elastic modulus? So we have seen that elastic modulus is like from the Hooke's law, stress is proportional to strain. So stress equal to E multiplied by strain. E is the elastic modulus. So E equal to stress divided by strain. So stress is F divided by area and strain is delta L divided by actual length. F, we are taking 3,500 divided by area. Area means the area of this cross section. So it is a circular type of cross section. So area is pi by 4 d squared. Pi by 4.6 squared. And strain delta L is 0.09 divided by length is given 12 mm. This 12 mm. So 0.09 divided by 12. Okay, so if we do this, stress will come 123.7 divided by 0.0075, and this value will come 16.49 gigapascal. So we have found out the elastic modulus. Now we need to find out the ultimate strength. What is the ultimate strength? Ultimate strength is like when we do the stress strain experiment, then first stress is linearly proportional to strain, and after that, after that there is yielding in the material. And after that, a point comes when the stress is maximum, maximum stress attained by the material. So this maximum stress is called the ultimate strength of the material. Stress strain plot. This is the ultimate strength. Okay, so now we need to find out the ultimate strength from this plot. So you can see here the maximum force we can see around here 5,400. So we'll take 5,400 Newton of maximum stress, and for ultimate strength it will be equal to 5,400 Newton divided by area. Area is 5 by 4 6 square. So it will come 190.98 megapascal. So this is the ultimate strength of this uniaxial compression test for this bone, for this femoral cortical bone. Okay. Now I'll explain some experiment which is performed in the bone for for extracting different material properties from the bone. So here in this figure, you can see there are two types of experiment, like two types of different experiment setup. Like first one is the 3-point bending, and second one is the 4-point bending. So here, what like this is how we do a bending experiment in if we want to find out the flexural rigidity for a bone. First we do the bending experiment, then we plot the shear force and bending moment diagram, and using those plots we can estimate the maximum bending load that can be carried by that bone. So first one is a 3-point bending, like the bone is supported in 2 points, then 2 points, then we apply load from the midpoint from the top. So that's why it is a 3-point. And in a 4-point, there are 2 points in the support, and the load is applied on the 2 points from above the bone. And here you can see that from the bending moment figure, the maximum bending moment is FL divided by 4 for the 3-point bending. And for the 4-point bending, the maximum bending moment is FA divided by 4. What is A? A is the distance between this point in which the load is acting and the supported, and the nearest point in which the bone is getting supported. And in the case of 3-point bending, L is the distance between the two supports. So now there are some assumptions for performing this type of bending experiment. Like here, the sample is straight, unstressed, and with uniform cross section, and the material is isotropic, linear, elastic, and homogeneous type of material. And a length to width ratio of 20:1 is recommended. Otherwise, shear force dominates, and crushing of loading points must be avoided. So these are some assumptions for doing this type of bending test. Now there is one problem related to bending of bone. So in this problem is given that a force of 4,000 Newton acts 60 mm from the axis of the structure, where we consider idealized bone cross-sectional area as illustrated in the figure. Now we need to first determine the moment of inertia and the maximum bending stress that this bone can withstand, the maximum amount of bending stress. Okay, the inner and outer radii for bone section are given. Ri is 20 mm and R naught is 25 mm. So here the force P is acting. Force P is acting at a distance of 60 mm, and the value of force P is 4,000 Newton. So what is the value of this bending moment M? M will be equal to P multiplied by 60 mm. So P is 4,000 Newton. 4,000 into 60 Newton mm. 24 240 Newton meter. We are converting mm into in terms of meter. So now we need to find out, or we'll keep it in mm only. 2.4 into 10 power 5 Newton mm. Okay, this is the value of bending moment. Now, the moment of inertia for a circular type of cross section is I equal to pi by 4 r to the power 4, where r is the radius of this cross section. So since the cross section is annular type, so the moment of inertia is I is the moment of inertia. Moment of inertia I. So here I will be equal to pi by 4 r not to the power 4 minus ri to the power 4 equal to pi by 4. We'll substitute r not 25 minus 20 to the power 4, which will be 181,132 mm. Okay, this is the value of the moment of inertia. And now we need to find out the maximum bending stress. We have calculated the value of moment of inertia. Now we need to calculate the value of maximum bending stress. So how we'll do that? So in the case of bending, assume this bending of this beam which is acted by a bending moment m. So this beam is getting deformed like in this manner. In this way, the beam is getting bended. So here there is one relation like which is known as Euler's equation, which is Euler's equation of bending, which is m by I sigma b by y, where m is the bending moment, I is the moment of inertia of the cross section, sigma b is the bending stress, and y is the like if we take this cross section of this beam as circular, so and this is the center point. So if we draw one axis, horizontal axis passing to the point, then this is known as the neutral axis. NA means neutral axis. In this axis, there is no bending stress. Bending stress is 0 in the neutral axis. Now, if we go means from the neutral axis, if we go towards upward, then this like it is a linear type of variation we get, and this distance from neutral axis, this is known as y. And you can see sigma b is directly from this equation, sigma b is directly proportional to y. So when y is means when the bending stress will be maximum, bending stress will be maximum on the periphery of this cross section at this layer, at this point the bending stress will be maximum. Okay, so we can use this equation from this sigma b equal to my divided by I, and we have we have calculated. So in the question, it is asking the maximum bending stress. So for maximum bending stress, this sigma B max is m. Y, the maximum value of y is radius of this cross section. Then I m, the value of bending moment is 2.4 into 10 power 5. And the value of r means the outer. Here you can see it is a type of annular cross section. So inner radius is ri and outer radius is r naught. So value of y is r naught. R naught which is, now we can substitute 2.4. R naught is 25 divided by I 181132. If we do this calculation, then sigma B maximum will come as 33.12 megapascal. Okay, so this is the answer. This is the answer for maximum bending stress that this bone can sustain in this loading condition, and this was the answer for the moment of inertia for this bone. There is one more problem in which okay, in this problem it is saying that femoral diaphysis is idealized as a circular cylinder with a periosteal diameter of 3 centimeter and then endosteal diameter of 1.2 centimeter. Calculate the diaphysial failure load for uniaxial compression and the failure moments for bending and torsion. This sigma FC means failure load for compression is given, failure load for CR for CR is given, and failure stress for bending is given. And the femoral length L is 42 centimeter, and femur is simply supported. We need to do this problem. So this is the stress for failure stress for compression. And this is the failure stress for shearing. And this is the failure stress for bending. Here the periosteal diameter means the outer diameter, and the endosteal diameter means the inner diameter. So first we'll do the first case, which is uniaxial compression. And one more statement is given, which says that cortical bones are strongest in compression, weakest in shear, and intermediate in tensile failure. So now we'll do first case, which is uniaxial compression. So in uniaxial compression, the femur will be simply acted by a compressive load, FC, and uh, which stress, failure stress we need to use? We need to use this sigma FC, which is the failure stress in compression, which is given 195 megapascal. So we will write sigma FC equal to FC divided by area of this bone. Okay, so FC, we need to find out the FC because sigma FC is given and area is given. Area is this diameter values are given. So it will be pi by 4 d naught square minus di square. Now, if we substitute sigma FC is 195 equal to FC divided by what is the value of this pi by 4? Outer diameter is 3 centimeter. So we'll write the units of length is in terms of mm. We'll convert this centimeter into millimeter. 30 square minus 4 square. So it is 593.76 mm square. So from here, FC is equal to 195 multiplied by 593.76 will come 3 centimeter. it is coming 115.78 kilonewton. So this is the value of compressive load which we can act during the uniaxial compression. Now next case we'll do for the bending failure moments for bending. So in this case, this is a type of 3-point bending. So in the case of 3-point bending, we have seen that the maximum bending moment was this 3-point bending. You can see the maximum bending moment is FL divided by 4. L is the length between the distance between the two supports. So here, second case is failure moments for bending. In this case, the maximum bending moment is FL divided by 4. Length, here we have to consider this length, the 42 centimeter, the model length. Okay, so failure bending moment is given, failure bending stress is given 208 megapascal. So we'll use this sigma B208. And we have seen one relation which was sigma BMI. Sorry, it is my by I. Okay, so we'll use this relation here, like sigma FB will be equal to mx multiplied by y max divided by I. So first we have to determine this moment of inertia I. I is here you can see the cross section is annular type of cross section. So I is pi by 4 r naught to the power 4 minus ri to the power 4 equal to pi by 4. R naught is pedestal diameter is given 3 centimeter. So R naught 1.5 centimeter, which will in mm 15 to the power 4 minus Ri is 1.2. It will be 0.66 mm to the power 4. So it will be 38742.9 mm to the power 4. So here in this equation, we can now substitute sigma FB, which is given 208 equal to mx, and in this case, the cross section is annular type of cross section, and from the neutral axis. This y max is value of r naught. So y max is r naught divided by 38742.9. So now if we solve this from here, we will get m max, maximum bending moment, because in the question it is asking failure moments for bending and torsion. So m max is equal to 208374.9 divided by r naught is 15. We do this, then it is coming 5 3 7 2 3 4.6 Newton mm, because we are taking the force unit in Newton and the length unit in mm. So this is the maximum bending moment that can be applied in the bone for this 3-point bending load. So now using this equation, m max equal to FL divided by 4, we can calculate the value of F, value of the force F. Here we can use 37 equal to F dot L. L is given 42 centimeter. So L is 420 millimeter divided by 4. From here, F will be equal to 5116.5 Newton. Okay. This is the maximum force which can be applied in this 3-point bending. Here you can see the force F is acting in this position. Like the bone is put in a horizontal position and it is supported in 2 points. And between the 2 points means in the mid between the 2 points from the equal distance from the 2 supports at the midpoint, we are applying a force F. So this value of F is 5116.5 Newton. Okay. So we have solved 2 cases, one for this uniaxial compression, then the second case was for bending, failure moment for bending. So now we'll solve this torsion, failure load for failure moments for torsion. So what is the torsion? We have seen bending. What is bending? So now torsion is when a shear stress is acting. Means shear force is when some torque is acting. That means this is a cross section and some torque is acting in this direction in the cross section, then because of this torque, there will be some shear stress which will be produced in this cross section. And now we need to check the maximum torque that can be applied in this bone for the given failure stress in torsion. And what is the value of that failure stress in shear? Failure stress in shear is given 69 megapascal. Sigma Fs equal to 69 megapascal. Okay, similar to the Euler's equation in bending, there is one equation in torsion which is T by Z equal to shear stress divided by the radius, means R is the radial length from the center. So here what is T? T is the torque, J is the polar moment of inertia, tau is shear stress, and R is the radial distance from the center. J is polar moment of inertia, T is torque, tau shear stress, R is the radial distance from the center. Okay, now so from this equation we will get tau, shear stress tau is equal to T multiplied by R divided by J. And in the given question, the cross section is a type of annular type. So in this case, the given cross section is like this. Inner radius is Ri and the outer radius is Ro. So for this case, the polar moment of inertia J is pi by 2 R naught to the power 4 minus Ri to the power 4. We will first calculate this value of J. What is R naught? R naught is 15 to the power 4 minus Ri is 6 to the power 4. This will be equal to 77485.8 mm to the power 4. Okay, now now we need to find out the maximum torque, maximum moment, maximum shearing moment that we can apply on this cross section. So we need to so for maximum torque, here the shear stress will be equal to the sigma failure stress for this material. So it will be sigma Fs equal to T multiplied by and R. What you will be R will be the value of R naught, the outer radius. So R naught is 15 multiplied divided by J, polar moment of inertia, 77,485.8. So here we substitute 69 equal to from this equation we'll get torque is equal to 356 434.68 Newton. And okay, this is the maximum torque or maximum moment which we can apply in the bone without getting means this is the limit of the when torque or limit of the moment sharing moment we can apply. So if you have any question you can ask. Do you have any doubt? You can ask. Okay, so we'll close today's class now. And next, I will meet on next Friday, on 10th of October from 6 same PM. Okay, thank you for joining today's class.